This is a story about a math problem so deceptively simple that a 5-year-old can understand it, yet so terrifyingly difficult that the world's greatest mathematicians have spent nearly a century trying to solve it, and failed. It is a mathematical trap. It's a loop that catches numbers and refuses to let them go, dragging them down to the exact same, predictable graveyard. The legendary mathematician Paul Erdos once looked at this problem and issued a grim warning to the scientific community. Mathematics is not yet ready for such problems. He genuinely believed that our current understanding of numbers, logic, and the universe itself is simply too primitive to crack it. Another mathematician, Geoffrey Lagarius, remarked that this single problem is an absolute obsession, capable of consuming a scientist's career and leading them into a psychological dead end. And yet, the entire problem is built on just two incredibly basic rules. Rules you learned in the first grade. Take any whole number you can possibly think of. If it's an even number, you cut it in half. If it's an odd number, you multiply it by 3 and add 1. That's it. Cut even numbers in half, triple odd numbers and add 1. Let's play out this game with a random, innocent number. Let's pick 7. 7 is odd. So, we multiply it by 3 and add 1. $7 times 3 equals $21, plus 1 is 22. 22 is even. We cut it in half, which gives us 11. Triple it and add 1. $11 times 3 equals $33, plus 1 is 34. 34 is even. Half of that is 17. 52 is even. Half of 52 is 26. 26 is even. Half of 26 is 13. 13 is odd. 40 is even. Half of 40 is 20. 10 is even. Half of 10 is 5. 5 is odd. 8 is even. Half of 8 is 4. 2 is even. And look what happens when we reach 1. 1 is odd. 4 is even, so we cut it in half to get 2. We are caught. We have entered the 4-2-1 loop. Once a number falls into this trap, it can never escape. It spins in this tiny, infinite circle forever. 4, 2, 1, 4, 2, 1, 4, 2, 1. The Collatz Conjecture is the assertion that every single positive whole number, no matter how unfathomably massive it is, will eventually crash down into this exact same 4-2-1 loop. It sounds like a fun little math riddle, a neat trick to show off on a chalkboard. But behind this simple exterior lies a cosmic mystery that challenges everything we think we know about the order of the universe. For decades, researchers have thrown the world's most powerful supercomputers at this problem. They have checked every single number up to 2 to the 68th power, that is a number followed by 21 zeros. A number so large that if you had that many grains of sand, you could fill the entire solar system. And every single one of those numbers, without exception, eventually gets pulled into the gravity of the 4-2-1 loop. But in mathematics, checking a trillion numbers, or a quintillion numbers, or even a septillion numbers is not a proof. In the infinite expanse of numbers, a pattern can hold true for a trillion miles, only to break apart on the next step. To truly solve the Collatz conjecture, someone has to prove that it is mathematically impossible for any number to escape. To understand why this is so monstrously difficult, we have to look closer at the journey these numbers take. The path a number travels under these two rules is rarely a smooth, gentle slide down to 1. Instead, it behaves like a chaotic, violent roller coaster. Mathematicians actually call these numbers Hailstone numbers, because their values rise and fall drastically in the atmosphere of the problem, much like a hailstone being tossed up and down inside a violent storm cloud, before finally plummeting to Earth. Take the number 26. It has a relatively calm journey. It goes down to 13, shoots up to 40, and then cascades down through 20, 10, 5, 16, 8, 4, 2, and 1. It takes just 10 steps to reach the bottom. But if you look just one step over, at the number 27, the universe seems to fracture into complete chaos. Let's trace 27. It's odd, so it goes to 82. Then 41. Then 124, 62, 31, 94, 47, 142, 71, 214, 107, 322, 161, 484, 242, 121, 364. Already, we are far higher than where we started. But it keeps going. It climbs up into the thousands. It hits 2,422. It drops down to 1,211, then shoots up to 3,634. It keeps climbing, defying gravity, scale, and logic, until it suddenly spikes at a staggering peak of 9,232. If you graph the journey of the number 27, it looks like the jagged EKG readout of a racing heart, or the map of a wild mountain range. It lunges frantically up and down across the number line. It seems completely random. It feels like a number that has successfully escaped the trap, soaring into the thousands, showing no signs of stopping. And then, right after hitting 9,232, it triggers a sudden, dramatic waterfall of even numbers. It plummets. It crashes down through the hundreds, through the tens, hits 16, 8, 4, 2, 1, and dies in the loop. It took the number 27 exactly 111 steps to find its way home. Why? Why does 26 fall so easily, while 27 explodes into a mathematical firework display before being dragged down to the exact same spot? There is no visible pattern. There is no formula that can look at a number and predict how many steps it will take to reach one, or how high its peak will be. Each number seems to possess its own unique, chaotic DNA. This brings us to the core of why the Collatz conjecture is a nightmare for mathematics. In math, we love predictability. We love functions where if you change the input slightly, the output changes slightly. But here, a microscopic shift, from 26 to 27, causes a catastrophic structural collapse in predictability. When you look at a visualization of thousands of Collatz sequences plotted together, something haunting emerges. If you map out the paths of all numbers up to 10,000, tracing how they link up on their way down to 1, you don't see chaos. You see an organic, breathtaking structure. It looks like a massive, glowing tree, or a map of rivers flowing down a mountain into a single ocean. Numbers are the streams, feeding into larger rivers, which feed into the massive Amazon River of the 421 loop. The structure looks intelligent. It looks designed. It possesses a strange, undeniable harmony. But we cannot explain why the tree grows the way it does. The history of this problem is a history of brilliant minds hitting a concrete wall. It was first proposed by a German mathematician named Lothar Collatz in the 1930s. Collatz was fascinated by the behavior of numbers when you repeatedly apply simple geometric or arithmetic rules to them. He scribbled the problem down in his notebook, passing it around to colleagues. For a while, it was just a quirky intellectual puzzle. But as the decades wore on, the puzzle transformed into a virus. By the 1950s and 60s, the problem had spread to universities across the globe. It went by many names: the Ulam conjecture, Kakutani's problem, Thwaites conjecture, Hosse's algorithm, or simply the $3 and $1 problem. It became so notorious at Princeton University and the University of Chicago that professors joked the problem was part of a secret Cold War conspiracy. The rumor went that the Soviet Union had deliberately introduced this unsolvable, highly addictive problem to American academics to completely paralyze Western mathematical research. Scientists would pick it up, think to themselves, "Oh, this looks easy, I can solve this in an afternoon," and then wake up 3 months later surrounded by stacks of wasted paper, having made absolutely zero progress. Shirzwa Kakutani, a world-class mathematician, confessed, "For a month everybody at Yale worked on it, with no result." A similar phenomenon happened at Chicago. So, why is it so hard? What is the hidden mechanism that makes this problem an unbreakable vault? To crack any mathematical mystery, you generally need to find a tool or a perspective that reveals an underlying order. With the Collatz conjecture, mathematicians have tried looking at it from every conceivable angle. The first approach is probabilistic. If you look at the rules objectively, it feels like the numbers should naturally shrink. Think about it. If a number is odd, you multiply it by 3 and add 1. That makes it an even number every single time. Because an odd number times an odd number is odd, but an odd number times an odd number plus 1 is always even. Therefore, every single triple and add 1 step, $3 and $1, is immediately followed by a divide by 2 step. If we combine those into a single action, the rule for an odd number is essentially $frac, 3 and 1, $2. When $n is a very large number, that $1 becomes practically irrelevant. So, the rule is effectively multiplying the number by $frac, 3, $2, or 1.5. On the other side of the equation, when a number is even, you divide it by 2, which is the same as multiplying it by 0.5. Now, in the infinite landscape of numbers, exactly half of all numbers are even, and half are odd. If you assume that a Collatz sequence acts like a random coin toss, flipping between even and odd with equal probability, then over a long journey, you will do the even step half the time and the odd step half the time. If you multiply a number by 1.5, and then multiply it by 0.5, what do you get? You get 0.75. Because 0.75 is less than 1, the number, on average, should shrink. Every 2 steps, a number should theoretically retain only about 75% of its previous value. This geometric decay means that if you run the process long enough, the numbers must eventually trend downward towards 0. And since they are whole numbers, they will eventually hit the bottom boundary, get captured by the 4-2-1 loop, and stay there. This statistical argument is incredibly convincing. It tells us that, on a macroeconomic scale, the Collatz conjecture must be true. The physics of numbers should force everything downward. But statistics are not a mathematical proof. Statistics tell you what happens on average, they do not tell you what happens in every specific instance. To break the Collatz conjecture, you only need to find one single exception. Just one. And there are 2 ways the conjecture could be false. The first way is if there is a number that enters a different loop. Imagine a number that, under these rules, cycles through a sequence like 50 to 100 to 200 and back to 50, completely separate from the 4-2-1 loop, never touching it. The second way the conjecture could fail is if there is a number that simply grows forever. A number that shoots off into infinity, climbing an endless mountain range, never hitting a waterfall of even numbers, drifting out into the dark cosmic void of the number line. Can we definitively prove that no such numbers exist? In 2019, one of the greatest living mathematicians, Terence Tao, a man often described as having the highest IQ in the world, decided to take a serious run at the Collatz conjecture. Tao didn't solve it completely, but he achieved the most significant breakthrough the world had seen in decades. Tao approached the problem by shifting the goalposts. Instead of trying to prove that all numbers reach 1, he used advanced mathematical analysis to prove that almost all numbers eventually reach a value that is much smaller than where they started. When mathematicians say almost all, they are using a strict technical term. It means that if you choose a random number, the mathematical probability that it obeys this rule is 100%. The exceptions, if they exist, are so incredibly rare that they have a density of 0 in the infinite sea of numbers. Tao's proof was a masterpiece of modern mathematics. It showed that the gravitational pull of the 4-2-1 loop is overwhelmingly dominant. It proved that if you pick a giant number, it is virtually guaranteed to shrink down to next to nothing. But even this monumental achievement left the core fortress unbreached. Tao himself admitted that his methods, as revolutionary as they were, still fell short of a total proof. The absolute truth of the Collatz conjecture remained just out of reach, protected by a fundamental limitation in human mathematics. Why does this wall exist? Why can our greatest minds map the distant edges of the observable universe, split atoms, and write algorithms that simulate reality, but fail to solve a puzzle based on primary school arithmetic? The answer touches on something deeply philosophical about the nature of mathematics itself. We tend to think of mathematics as a pristine, completed cathedral of logic. We assume that if a statement is true, there must be a clean, logical pathway of steps that proves it. But in the 1930s, around the exact same time Lothar Collatz was writing down his conjecture, a logician named Kurt Gödel blew that assumption apart with his famous incompleteness theorems. Gödel proved mathematically that within any consistent logical system, there will always be statements that are undeniably true, but completely unprovable using the rules of that system. There are truths that sit in the dark, forever beyond the reach of a formal logical ladder. Many modern mathematicians suspect that the Collatz conjecture is one of these unprovable truths. The reason lies in the toxic relationship between addition and multiplication. Human mathematics is exceptionally good at understanding multiplication on its own. We have prime numbers, which are the fundamental building blocks of all numbers through multiplication. Every number can be broken down into a unique product of primes. If you stay within the realm of multiplication, the patterns are elegant and predictable. If you add numbers together, the progression is linear, clear, and easy to trace. But the moment you mix addition and multiplication together in a recursive loop, the universe breaks. The Collatz conjecture forces these two worlds to collide at high speed. The even rule, divide by 2, is a purely multiplicative operation. It alters the prime factorization of the number, neatly stripping away a factor of 2. But the odd rule, multiply by 3 and add 1, mixes multiplication with addition. That tiny, seemingly innocent one is a grenade thrown into the system. When you multiply a number by 3, you are working with its prime structure. But when you add 1 to that result, you completely shatter that prime structure. You randomize it. The new number's prime factors bear absolutely no relation to the prime factors of the number you started with. Every time a Collatz sequence hits an odd number, it shuffles the deck. It randomizes the number's mathematical identity. The sequence becomes a chain of unpredictable mutations, alternating between orderly division and chaotic scrambling. Because of this constant scrambling, we cannot build a coherent mathematical bridge between the starting number and the final destination. We are trying to use a language of order to describe a process that actively destroys order at every turn. If the Collatz conjecture is truly unprovable, it means we could spend the next 10 billion years checking numbers on quantum supercomputers, finding that every single one of them collapses to 1, without ever being able to write down a definitive proof as to why. It would mean that the universe has coded a rule into the fabric of reality that we are allowed to see, allowed to verify, but forbidden to fully understand. This is what makes the Collatz conjecture so beautifully terrifying. It is a mirror that reflects the limitations of human intelligence. It stands as a humbling reminder that just because a question is easy to ask, it does not mean it is easy to answer. It exposes a profound truth, that we are still children playing with blocks in the foyer of mathematics, looking up at a grand, towering mansion whose upper floors are still completely lost in the fog. The problem remains open. Right now, on desks and chalkboards around the world, students and professors are scribbling down numbers. They are cutting them in half. They are tripling them and adding 1. They are watching them climb like hailstones into the thousands, hoping against hope that they will be the one to find the number that flies away into infinity, or the one to finally build the bridge that explains the chaos. But until that day comes, the loop is waiting. Pick a number. Any number. Multiply by 3, add 1. Cut it in half. And watch as it falls, inevitably, back down to 4. 2. 1.